Hello and welcome to my talk, NIF or NIF C. I'm Andreas Rumpf, the inventor and lead developer of the Nim programming language. So I'm actually the reason why we are all here. And this talk is about Nim's compiler development future. We want to make the Nim compiler faster, use less memory, and have an order of magnitude fewer bugs. And we will accomplish this by using good design, and this good design eventually became NIF, which is a new data format for interoperability between programming languages and specifically inside a compiler between the different compiler phases. So, but the primary motivation was to add IC to Nim. IC is incremental compilation, so the goal is that when you recompile your program, only the parts that did change actually get recompiled to speed up the process. And we will accomplish this by precompiling Nim modules to NIF. And then when you import a module, then it won't be compiled again, but instead the precompiled version will be loaded into the compiler. And also this in a most lazy fashion by embracing POSIX mmap call, or the Windows equivalent. So this is implemented in Nim's standard library in the memfiles module. Okay, so NIF stands for Nim Intermediate Format, and this is now a text-based format. In the past we used binary files, or tried to use binary files, but it turned out that at least the binary files, the way I designed them, weren't really suited to this lazy loading mechanism via mmap, and also they were very hard to debug, because eventually a Nim identifier or a name becomes a pair of numbers, and then if it doesn't work, you get some lovely compiler internal errors telling you that this ID doesn't exist. And then you need to first figure out what does this ID actually mean, what kind of symbol was that originally, and then you need to see where did it go wrong. Was it the storing mechanism or the loading mechanism? And you need you can then look at the stored file, but it's in a binary file, so you need a program to translate this binary form into a somewhat more readable form. But then you might get overwhelmed because that expanded in size so much. So, and also it makes things slow, because it turns out the mere fact that you produce megabytes of data, where it's kilobytes of data in the original Nim source code, this can be slower than just recompiling the module from scratch. So the Nim compiler is actually quite fast. Everything we do to speed it up must be better than what we currently do, and currently we're already quite good. Okay, so now a text-based format, because it usually takes up less space on the disk, so it's faster to write, and it's also faster to load. And also, as I said, this time we will use mmap. Okay, so here we have, and NIF is just Lisp, so it's a text-based format that is still kind of readable, as you can see. So this is here an Hello World example, and everything we use here in this example needs to be declared. So we import a type, and then we import this proc write.1.sys, and we say it takes var args and also a parameter of type file, and then we call this write_sys hello world. And the idea here is that in NIF there is no overloading, so every name is uniquely determined, and also the names must still be short. So the way we do this is to say we take the nim word or the nim name, then we append a unique number. So this is the first write proc in system. That's the idea. And the final part of this is the module where it came from, or rather a short version of this module name. But it's also unique. So if you have lots and lots of say utils.nim files, modules in your project, and these are all different in different paths, then they will produce a unique name. So and still be short. So that's taken care of. And finally, what's very important or what's very interesting to look at here is this 2,5, sysio.nim. This is line information, so this means this type node, AST node here, actually comes from column 2, line 5, and the file is of the file sysio.nim, originally in the nim code. Okay, so it's a Lisp, and even a Lisp has a way to form tokens, and then these tokens produce trees. So we have the usual tokens. We have string literals, we have integer literals, floating point numbers, identifiers, and symbol. A symbol is an identifier that was bound to some declaration, so it's unique. And the parentheses are then used to group these things into trees. Numbers must start with either the plus or the minus, so that it's not ambiguous and cannot be confused with the source line information here. Because again, source line information is very important to get right, as it easily takes up 50% or more of the final resulting file. And this problem is not specific to NIM. If you look at how, for example, these source maps, they're called in JavaScript work, they also went through a couple of iterations to get the format right so that it doesn't take up too much space. All right, so here is an excerpt of the NIF grammar. The point here is that it's a very simple language. The full grammar would still fit on the slide, I think, but I haven't really tried. So the point is, it's very simple. It's not ambiguous, can be parsed very quickly, and you can parse, let's say, slices of it individually, so so that this memmap mechanism works. Okay, this is now NIF C. NIF C is NIF in a special format, or let's say it's a dialect of NIF. So NIF doesn't, so these what comes after the parentheses open, these are called node tags, and they are different depending on which NIF dialect you are looking at. So this NIF dialect called NIF C is the goal here is to translate NIM code into something that is close to C, but a little bit easier to generate, so that we split up the task of producing C code into individual compiler passes that are easy to understand and easier to get right. So so this is a real example. This was also shows a little bit more than just hello world, but instead it also shows assignment to an object field here, and a return instruction. And what sticks out are these dots. A dot in NIF is just a shortcut for an empty node. And these empty nodes, they help us in making the AST regular. So for instance, you can here say a proc node has always 1, 2, 3, 4, 5 children. And some of these children can be empty, but it's always 5. So that again makes it easy to process internally. And in this case here, we don't have any named parameters. We only have the return type that is an int with 32 bits, but it takes a variable number of arguments, but this is then encoded in the pragma section. So the parameters are empty and the function body is empty. Okay. And apart from the fact that NIF C uses the NIF Lisp syntax, it's actually quite close to C while at the same time avoiding C's design bugs. So arrays do not decode into pointers. Arrays are value-based data types that that can be returned from a function, etc. The messy declaration syntax of C is gone because we use NIF syntax. And we have some basic form of inheritance in NIF C because I think that's much more elegant than C's solution. C's solution is some weird special rule in its specification that deals with aliasing restrictions and what is allowed to alias what else. So basically, there is a rule in C that says if you have a struct, the first field of the struct can alias the full struct itself and vice versa. And this is then used to emulate inheritance. And this mechanism is very important because the C implementation of Python, for instance, or the GTK framework, these huge C projects, they wouldn't even work without this rule. And yet I'm sure most of you didn't even know it exists. So it's a very important rule that kind of, let's say, hacks inheritance into C's design. And I prefer to make this explicit instead. So NIF C offers inheritance. And also for the reason that, again, we also want to be able to translate NIF C to C++, which also offers inheritance. Okay, and NIF C is easier to generate than raw C as it's a Lisp. And there is a different or another nice feature that the NIF C tool compiler, let's say, allows for an arbitrary order of declarations. So if you need to produce a graph, a type graph, where a struct contains a different struct, which then contains a pointer to something else, there is in C some complex mechanism that you can actually use things before they are declared, as long as it's just a pointer to it, roughly speaking. And for the Nim compiler, that's also quite hard to get right. So we delegate this task of getting this right to NIF C instead. Okay, so we use NIF for this IC feature. This is this gear 2 here in this diagram. And then we use NIF to generate C code for us in this NIF C dialect. Eventually, there will also be gear 4 and gear 4 steps. So the idea is to split up the backend further into well-defined phases, where every compilation phase has a NIF input and a NIF output, but there is a specification. Like there's actually a grammar and a tool NIFgram that can translate a NIF grammar description into a Nim program that checks for consistency with this grammar. So and again, the idea is that we make the compiler easier to understand and easier to get right eventually. But So this gear 2 here is in heavy development. This is the IC feature. And once that is complete, we won't have a full NIM compiler with IC, but we will have a semantic checker with IC for NIM. And that's already very useful to give us a better NIM suggest feature, because then NIM suggest can become a tool that you run once per query, and after the query is done, the query is something like list me all the occurrences of this NIM identifier. So where in my program is this NIM identifier used? And then this gear 2 tool would list all the occurrences and then or find all the usages, and then would die. And if you then ask, go to this declaration, where is it? Where can I find the symbol? It would be a different program invocation for this gear 2 tool, and it would be fast enough so that it doesn't matter. So this would avoid this whole NIM suggest problem, that NIM suggest must run as a service, and then it keeps growing its memory consumption, and eventually it crashes because something internally went wrong. All these programs will disappear by design, because we won't have a service but a one-shot program instead. Okay, so this here is also, this is implemented like NIF C. It's a thing, you can compile it already, you can try it out. You can also add native code to it. So here is some lovely, what's up with this browser? Okay, so here is this idea that you can actually produce machine code directly from NIF C. You don't have to produce C code from it. And here is the plan of how to accomplish that. If you want to help out, contact me. I can give you exact instructions how it must be done. It's just that I lack the time to do it myself. Okay, gear 3. Let's see if this would then do iterator inlining, mutability checking, injects the copies where NIM needs them, or rather tries to optimize them out, and would eliminate expressions. But these details are not important. The gear 4 would eliminate exception handling and perform destructure injections. Gear 5 would then be the final to NIF C pass, so which basically at this point then is so simple that you only need to rename a couple of symbols, so that this works out. But the point is, by splitting it up into these different steps, we create a more maintainable compiler, which can be tested in like all these phases can be tested individually. You can write test cases for these steps. And also, because we have this is all based on NIF, which is a text-based format. And then you can also switch the implementation. Like, for instance, if you find a better algorithm to inject destructors into NIM code, you could then only replace this the corresponding gear phase without having to touch any other part of the NIM compiler. You could also dream of something that the NIM compiler itself is just basically a shell script that puts these two different programs together via Unix pipes. It's also conceivable. Finally, this allows us also to evolve the NIM language further, because we like, if you have NIM version 3, then eventually, who knows, we would only need to replace this SEM phase here, which is basically the front end, or parts of the front end, whereas the rest of the compilation pipeline would remain identical. So that's my talk. Thank you for your attention, And I'm going to leave this slide open for a couple of minutes because I think it's the most useful for the questions you might have.